The carbonyl group present in aldehydes, ketones, carboxylic acids, and carboxylic acid derivatives is probably the most important in organic chemistry. The carbonyl group is the most important functional group in organic chemistry because of its fascinating display of chemistry, because of its exceptional reactivity, and because of the wide range of reactions that it can undergo. The carbonyl group is so versatile. It's chemically versatile, which means it can be transformed into other organic compounds, which can be in turn further elaborated into useful, complicated or complex or target molecules of medicinal, chemical, or biological interest or applications. Let's draw a general structure for aldehydes in order to illustrate or revisit the electronics of the carbonyl group. So this is the general structure of aldehydes. Now, if you look carefully at this carbon-oxygen double bond, oxygen is more electronegative than carbon, which pulls electrons toward itself in this chemical bond. So we can denote this difference in electronegativity between oxygen and carbon, if you like, the unequal shift of electrons, polarity of this carbon-oxygen bond, or polarization actually by this conventional arrow, or using the delta notation. This unequal shift of electrons, or the shift of electrons by oxygen more than that of carbon, leaves a delta positive, if you like, or a positive partial charge on carbon, and delta negative on oxygen, or a negative partial charge on oxygen. Now, clearly, this positive character, if you like, or the positive charge of carbon attracts nucleophiles. It attracts nucleophiles with opposite charges, and that's exactly one reason, if you like, why organic reactions take place, is because of attractions of charges, attractions of dipoles, if you like. So this is inductive effect, inductive withdrawal, which makes that carbon of aldehydes, in this case, and also ketones, electrophilic at carbon of the carbonyl group. Not only there is inductive withdrawal, there is also resonance withdrawal. We can also draw another resonance structure by breaking that carbon-oxygen double bond and releasing the two electrons on oxygen. Therefore, we can draw another resonance structure, another resonance form for this general structure of aldehydes. If you look at that resonance form, it's clear that that carbon of this general structure of aldehydes is electrophilic. It is electrophilic. So this carbon, therefore, is electrophilic. So this electrophilicity of carbon is induced not only by inductive withdrawal, but also by resonance withdrawal, and therefore carbon of carbonyl groups, specifically aldehydes and ketones, is susceptible to nucleophilic attack. Now, it is susceptible to nucleophilic attack not because of these two electronic effects. In other words, organic reactions do not necessarily take place due to attraction by opposite charges, but also by overlap between the HOMO orbital in a nucleophile with the LUMO orbital in an electrophile. If we draw the carbonyl group like that again, we can actually indicate the LUMO with something like that. So this is the LUMO orbital, and this is the p orbital on oxygen, and this means that the coefficient of this LUMO is actually greater at carbon. So this is like the pi star anti bonding orbital. It's unfilled, it's empty. So this is the empty pi star orbital. It is the LUMO, and this LUMO orbital has a greater coefficient at carbon, and that's because of the difference in electronegativity. Now, this LUMO interacts this LUMO in this electrophilic carbon interacts with the HOMO orbital coming from a nucleophile. So HOMO-LUMO interactions, if you like, or overlap is another reason why organic reactions take place, especially in this case, in the case of carbonyl groups. We can therefore represent the nucleophilic addition reaction by a general reaction like that. So that's the aldehyde again. Now we have already established that that carbon is electrophilic due to inductive withdrawal and resonance withdrawal, and also nucleophiles can attack that carbon because of the HOMO-LUMO interactions. So a general nucleophile, something like this, will now approach and attack the aldehyde. The question is, at what angle? Well, it's already been established, okay, that nucleophiles attack carbonyl groups at a specific angle, which is called the Bürgi-Dunitz angle, which is 107 degrees. So the nucleophile attacks at an angle like that, which is 107 degrees. So that's the nucleophilic attack, the nucleophilic angle of attack. If the nucleophile attacks, it will attack that carbon in nucleophilic addition reaction, and if that happens, the carbonyl group obviously breaks, the pi bond breaks, and electrons are released on oxygen. Now, as a result of this nucleophilic attack, it's also called nucleophilic addition. An intermediate is formed, which is the corresponding alkoxide. So that's the intermediate that's produced, in this case, in this nucleophilic addition reaction. We can describe this as nucleophilic addition. Now that intermediate alkoxide, the result of the nucleophilic addition, attack of nucleophiles on carbonyl groups, gets protonated in a subsequent step. So, and that's of course done by treating that alkoxide with a proton or a proton source, and the product, the final product, is the one that is shown. So this is a general scheme for nucleophilic addition reactions of aldehydes and ketones. Nucleophiles attack that electrophilic carbon either because of attraction of charges. Negatively charged nucleophiles can get attracted to that positively charged carbon. A reaction can take place, or a reaction can take place because of the HOMO-LUMO interactions, if you like, overlap between the HOMO of a nucleophile with the LUMO of the carbonyl group, which has a greater coefficient at carbon, as we've seen before, and that's due to the difference in electronegativity. The nucleophile approaches at 107 degrees. It attacks that carbon. The carbonyl group breaks up. 2 electrons are released on oxygen. That intermediate alkoxide is then formed, which gets protonated in the last step. So this is the overall scheme of nucleophilic addition reactions.